we're going to be talking about gravitational potential energy. Now, yesterday, or the previous video, we did gravitational potential. But today we're going to be doing gravitational potential energy. So if you remember yesterday, or the previous video, we did gravitational. So we did gravitational potential. And that was equal to work done per unit mass. Work done per unit mass. So we want to work out work done. Work done is quite similar to energy. The units is the same. So the units for energy is work done is equal, and that is joules, isn't it? All right, so what was the equation for gravitational potential? It was, remember, it was Vg. The symbol for gravitational potential was Vg is equal to minus Gm over R. So that was gravitational potential. However, we want gravitational potential energy. Gravitational potential energy. Now, to work out gravitational potential energy, because this is work done per unit mass, we want to work out work done then. So work done is equal to gravitational potential times by the mass. So what do you end up? Well, you end up with m times Vg. So that is work done, or energy. In full, that would be Gmm over R. Okay, so let's draw a diagram and see what we mean. So suppose that this is the surface. So this is the surface. So this line is the surface. So this is the ground. This is ground. Now here, let's just say that this is A, assuming this is horizontal, and this is another horizontal line B. Now at point A, where it's equidistant, assuming that it's parallel, so assuming these are the field lines. Suppose you move an object. So this is an object. So this is object at level A, and you're moving the object to level B. Because you're moving against the gravitational field, you are doing the work. So from A to B, you're doing the work. So here, let's just say you've got gravitational potential at B. So you've got a gravitational potential at B. So let's just say that this is Vg at B. And this is Vg. This is the gravitational potential at A. Gravitational potential at A. Now, what is the change in the gravitational potentials? So when you do the change, so this is the change, the symbol for change in gravitational potential, and when you times that by m, the mass of the objects that you're moving, that will then give you the gravitational potential energy. So that will give you energy in terms of gravity. So you times m with the change in gravitational potential. And this is the gravitational potential energy. So because you're doing work, this is because the center of the planet is here, assuming this is not to scale. So the center of the planet is here. Now, because you're doing it just focusing on the surface, they are roughly parallel to each other. Obviously, if you're looking from space, it will look very radial, meaning that the lines are going in towards the center, so they won't look equidistant. But if you were to zoom in and you're looking at it, let's just say you're lying on the grass and you're looking at the surface, the lines look very, very parallel. So what I mean is that when you move an object from A to point B, because you're moving against the gravitational field, you're doing work. You're putting energy into the object to move from A to B. Now, because at point A, there's a gravitational potential. At B, there's a gravitational potential. And there's a change in the gravitational potential. And that gives you, when you multiply that by m, the mass of the object, that will give you the gravitational potential energy. All right, now let's try using the gravitational field strength. Now, what is the equation for gravitational field strength? If you don't remember, if you just remember that weight is equal to mass times g, where g is the gravitational field strength. Weight is a force, so F. So F is equal to mg, so g is equal to F divided by m. Now, what's F in terms of Newton's law of gravitation? So F is equal to big G times m1, m2 over r squared. And if you're dividing by one of the m's, so G is equal to big G times big M over r squared, one of the masses. Okay, so what do we do next? All right, so what is that in terms of Vg? So Vg was, if you remember that Vg was equal to work done divided by unit mass, and that was equal to minus Gm over r, wasn't it? So that was, so this was gravitational potential. This is gravitational field strength. So what is G in terms of Vg? One of the r's have cancelled. So what we have here is that G is equal to, so what's G in terms of Vg? It's minus Vg divided by r, isn't it? So it's minus Vg divided by r. And what is G? G is also equal to F divided by M. So that is equal to F divided by M. So now what do we do? Now let's just cross multiply and see what we get. So therefore, Vg so we get mVg is equal to Fr. And what is Fr? Now there's a minus missing. We can just put minus here, we can put minus there. And what is Fr? Force times distance. This is work done. So that is equal to work done. So the energy needed to move a mass against a gravitational potential is the same as the work done. All right, if we look at an example question, we have a forklift truck and it lifts an object of 80 kilograms, 2.5 meters from the surface of the earth. The mass of the earth is about 6 times 10 to the power of 24 kilograms, and the radius is 6,370 kilometers. What is the difference in potential, and therefore work out how much work is done? All right, so this is an example question. How would you go about answering this question? Okay, so first, let's work out the gravitational potential. So we need to work out the difference in Vg. Now, what is Vg? So Vg is equal to minus Gm over R. So assuming that the radius of the Earth, so assuming that you're on the surface of the Earth, and the radius is 6370. So the first R would be, so R1 would be 6370, 6370. And what's R2? R2 would be, you add 2.5 to it, because that will be extremely tiny. So that would be 6, well, convert that into meters, isn't it? 3 zeros, not 4. So then that will be 6370002.5. So those will be your different values for R. And in this case, what is M? Okay, so M in here, this case, is the mass that's producing the field. So this is the mass that is producing the gravitational field. The gravitational field. The mass producing the gravitational field. So in this case, it's the mass of the Earth. All right, so let's put the numbers in. So let's work out the change in gravitational potential. So because you're working out the change, the magnitude doesn't matter. So you know what's G? G is 6.67 times 10 to the minus 11. You times by the mass of the Earth. The mass of the Earth is given. It's roughly 6 times 10 to the power 24. So times by 10 to the 24 times by 6. And you're dividing it by 6370000, and you're taking it away from, again, it's the same, the top, but the bottom's different. So 6370002.5. All right, so let's work this out using a calculator. So we can take the top bit out. So 6.67 times 10 to the minus 11, and you're multiplying it by 6 times 10 to the power of 24. So that's outside the brackets. And then I'm doing 6370000 to the power of minus 1 minus 6370002.5 to the power of minus 1, and close brackets. So that gives you 24.656. We can do it to 2 decimal places. So 24.66. So this is 24.66. Now, because the gravitational potential is work done per unit mass. So what's the unit? It's joules divided by kilograms. And what's the mass? The mass is 80 kilograms. So you times that by 80. And what does that give you? That gives you 1,972. So let's do it to the nearest whole number, 1973. So M times Vg gives you 1973 joules.